Ever wonder why your coffee stays hot in a thermos while the rest of the world gets cold? Let a Eurostrade uncover the physics that keeps it steaming. A thermos works by reducing the three main routes of heat loss: conduction, convection, and radiation. Inside the container, a thin metal wall is separated from the outer shell by an evacuated space that eliminates air molecules. Because there are no molecules to collide with, conduction through the vacuum is almost zero, keeping hot coffee from losing energy directly to the walls. The inner surface of the thermos is coated with a reflective layer that reflects infrared radiation back toward the liquid, minimizing radiative heat loss. Convection is suppressed because the evacuated gap prevents fluid motion. There is no circulating air to carry heat away from the cup. The outer shell is usually made of stainless steel or insulated plastic, which has low thermal conductivity and adds another layer of resistance to heat flow. Together, these features create a high overall thermal resistance that slows down the rate at which the coffee cools. As a result, the temperature difference between the liquid and its surroundings decreases more slowly than it would in an open mug. The thermos essentially traps the energy inside until the user decides to drink the coffee or the container is opened. Even after several hours, the internal temperature remains noticeably higher, because heat transfer has been interrupted at every stage. This principle is why thermoses are also used for storing cold foods. They keep temperatures stable by blocking all three heat loss mechanisms. Understanding these mechanisms helps explain why a simple design can preserve hot beverages for extended periods. Pause 0.8. A thermos keeps coffee hot by minimizing heat transfer through its walls, which are engineered to interrupt conduction. The first layer is a thin metal shell that reflects radiant energy back toward the liquid. Next, a foam insulation surrounds the metal. Its many trapped air pockets act as thermal barriers. Because air is a poor conductor, heat must diffuse through multiple layers of gas before reaching the outer wall. The innermost surface also has a vacuum gap. Without molecules to transfer energy, conduction drops almost to zero. Radiative heat loss is countered by the metal's reflective coating, which sends infrared radiation back into the cup. Convection inside the thermos is limited because the narrow opening restricts airflow, keeping hot air from escaping. In contrast, a regular mug has solid walls and an open top, allowing heat to conduct and convect freely. Thus, the layered construction of a thermos creates multiple barriers that each reduce one mode of heat transfer. The result is a cup that stays noticeably warmer for hours, giving you more time to enjoy your brew. Pause 0.8. When a thermos is sealed, the space between its inner and outer walls becomes a vacuum. A vacuum contains almost no molecules to carry heat by conduction, which is the dominant mode in solids. In contrast, a foam or solid wall still allows some conduction through its material because atoms are close together. Convection requires fluid motion. Inside a sealed thermos there is no airflow, so convection is also suppressed. Radiation remains the only significant heat transfer mechanism across the vacuum gap, and it follows the Stefan-Boltzmann law. The thermal resistance of radiation can be expressed as R rad equals 1/I circumflex micro if T hot 3 plus T cold 3, where I circumflex micro is emissivity. For a typical foam, the conduction resistance is R cond equals L/K, with K around 0.03 W/m A circumflex K for polyurethane. Because K is so low and L is small, foam still offers less resistance than a vacuum, which has no K value at all. Graphically, the heat transfer rate Q equals I circumflex T/R total shows that the vacuum curve lies far below the foam curve for the same temperature difference. Thus, a thermos with a vacuum layer keeps coffee hot longer because it minimizes both conduction and convection, leaving only weak radiative losses. Pause 0.8. When coffee sits in a thermos, it loses heat mainly through radiation, not just conduction or convection. Radiation occurs as infrared photons that travel from the hot liquid to cooler surfaces inside the container. A shiny inner lid reflects many of these photons back toward the coffee, reducing net energy loss. The reflection works because metals and polished plastics have high reflectivity in the infrared spectrum. Each bounce between the liquid surface and the reflective lid keeps photons trapped within a small volume. Matte lids, on the other hand, absorb most of the radiation, converting it into heat that warms the lid itself. That absorbed energy then slowly leaks back to the coffee through conduction, speeding up cooling. By using a reflective lid, the thermos effectively creates a low emissivity boundary around the liquid. Low emissivity means fewer photons escape, so the temperature drop is slower and the coffee stays hot longer. This principle is similar to how Euro's glazed windows keep buildings warm by reflecting infrared back inside. Pause 0.8. When you pour coffee into a thermos, the liquid aerostrade as thermal mass immediately starts to resist changes in temperature. Thermal mass is simply the product of the amount of substance and its specific heat capacity, which for water euros rich coffee is about 4.18 a circumflex euros J/G a circumflex degrees C. A larger volume of coffee therefore contains more energy that must be removed before a noticeable drop in temperature occurs. The thermos aerostrade as inner surface limits conduction by keeping the metal wall at a nearly constant temperature, so heat transfer from the liquid to the exterior is slowed. Convection inside the cup also plays a role. A thicker layer of coffee reduces the rate at which hot fluid mixes with cooler layers near the walls. The insulating foam or vacuum gap in the thermos further suppresses both conduction and convection by creating a barrier that requires more time for heat to escape. As a result, a 400 circumflex euros ml cup inside a euros insulated container will stay above 70 circumflex degrees C longer than a 200 circumflex euros ml cup under identical conditions. Graphs of cooling curves show the 400 circumflex euros ml line staying higher for several minutes before converging with a smaller volume curve. This effect is purely mechanical. It depends on mass, specific heat, and the efficiency of thermal barriers, not on any exotic chemistry. Understanding these principles helps you choose the right cup size and container to keep your coffee at the desired temperature. Pause 0.8. Pre-euros heating the thermos is the first step to lock in heat. A warm container reduces the temperature gradient. Pour freshly brewed coffee into the pre-euros heated vessel, letting it sit for 30 seconds so steam condenses inside. Seal the lid tightly. A snug seal prevents cold air from entering and keeps heat trapped by conduction. Fill the thermos to at least 3/4 full. Empty space allows hot air to circulate, improving overall retention. Avoid frequent opening during transit. Each exposure to ambient temperature creates a heat loss spike. If you must check the temperature, open only for a few seconds and close immediately to minimize exchange. Use a thermos with euros walled stainless steel. This design reduces thermal conduction from the outer environment. Consider adding a small layer of foil or a euros retained sleeve around the lid to further block convection currents. Finally, keep the thermos in an insulated bag. This secondary barrier protects against rapid temperature changes. By following these steps, your coffee will stay hot for hours while maintaining flavor and safety standards. Pause 0.8. A thermos keeps coffee hot by interrupting all three modes of heat transfer. It uses a vacuum to eliminate conduction and convection, a reflective interior to bounce infrared radiation back into the liquid, and the coffee eurostrade's own thermal mass slows temperature decline. Together these mechanisms explain why your brew stays warm for hours.